Hello friends, Mr. Burrell here. We're in this unit on probability. We've talked about set notation, and then we've talked about some basic principles about probability using set notation. We've talked about what probability is, how we calculate probabilities. Now we're going to talk about probability in association with two-way tables. Two-way tables, or otherwise known, sometimes I'll refer to them in this video as two-way frequency tables, are a popular and helpful way of representing data, representing different sets and different values. And because they're used so often, we are going to talk about them and how we can use those tables to compute probabilities. So this is what I want you to be able to do by the end of this video. I want you to be able to construct a two-way frequency table given data points, compute individual probabilities given a two-way frequency table, compute probabilities for intersections of events given a two-way frequency table, and compute probabilities for unions of events given a two-way frequency table. So we've already talked about intersections and unions, so now we're going to talk about finding the probabilities of intersections, probabilities of unions from a two-way table. We're going to construct a two-way table, talk about what it is, and then calculate other individual probabilities with these tables. Okay. So first, some definitions, some things that we'll see in these two-way tables. Two events are mutually exclusive if they cannot both occur. So the example that I'm going to be using in this video is that of drawing a piece of candy, either like an M&M or a Skittle. We're going to be talking about with M&Ms and Skittles. So two events are mutually exclusive if they cannot both occur. For example, if you draw a piece of candy out of a bag, it can't be an M&M and a Skittle. Those are mutually exclusive events. Here's an M&M, here is a Skittle. You can't draw a candy and have it be both an M&M and a Skittle. It doesn't make any sense. So those are mutually exclusive events. Two or more events are said to be overlapping events if one or more events can occur at the same time. So example, if I were to just draw a piece of candy from a bag, if I were to draw a piece of candy from a bag, it can be both an M&M and red at the same time. Say we're identifying the event of drawing a red candy or drawing an M&M candy. You can have a red and an M&M candy because some of the M&Ms are red. You have some Skittles that are red, but you can draw an M&M and a red at the same time because there are red M&Ms. So that's what an overlapping event is, if one or more events occur at the same time. Okay, so if we were in person, we'd be doing this activity. So I'm going to kind of do the activity by myself and have you kind of follow along. So if we were all here, I would give each of you in groups a bag of M&Ms and a bag of Skittles. And this is what we would do. We'd collect data. I want you to count the number of M&Ms and Skittles of each color in your bag and record that information in the frequency table below. Then either enter the data on your teacher's computer or give the data to your teacher, blah, 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 blah. We're going to do all that. So what you would do is you'd list the number of red, orange, yellow, green, blue, and brown M&Ms that you have, and the number of red, orange, yellow, green, blue, and purple Skittles that you have. Okay, so for example, here are my M&Ms and Skittles. You notice I've opened up my handy little bags of M&Ms and Skittles. Here are my M&Ms over here. I have 3 oranges, 1 red, 4 greens, 4 blues, and 3 browns. And then over here in my Skittles, I have 1, 2, 3, 4, 5, 6, 7, 8 oranges, 2 greens, 2 yellows, and 2 purples. These are purple. They look kind of brown. Those are purple Skittles. So this is my little experiment. These are my 2 bags of M&Ms and Skittles and how many of each color that I have here. Okay, here's this table filled out for me. Again, I had 1 red M&M, 3 orange M&Ms, 0 yellows, 4 greens, 4 blues, 3 browns, for a total of 15 M&Ms. Then I had, with my Skittles, 0 red Skittles, 8 oranges, 2 yellows, 2 greens, 0 blues, and 2 purples, for a total of 14 Skittles. Okay, so those were all mine. So what I would do, my next step here would be to create a two-way frequency table. So when I say a two-way frequency table, this is what it is. I'm just going to read this definition real quick. We can combine individual frequency tables into a two-way frequency table. In this case, the rows here represent the types of candy, and the columns represent the color of those candies. And then it says, use the combined class data to fill in the two-way frequency table shown. Be sure to total each column and row. So what I would do is, if everybody was here, I would total everybody in the class's M&Ms everybody in the class's Skittles and put them in the corresponding columns here. So what I did is I used a random number generator to randomly select 7 different groups of different colors of M&Ms and Skittles as if I had done this in class, and this is the data that I came up with. So this is our figurative class's collection of Skittles. So our class had 51 red M&Ms, 27 red Skittles, 33 orange M&Ms, 58 orange Skittles, etc., etc., etc. Notice that nobody had any purple M&Ms because there are no purple M&Ms. There's only purple Skittles. And no one had any brown Skittles because there aren't brown Skittles. There are brown M&Ms. And then down here I have the total of all the reds, the total of all the oranges, yellows, greens, blues, purples, and browns of both M&Ms and Skittles. And then I have the total M&Ms of all colors, total Skittles of all colors, and then the total of all M&Ms and Skittles, the total number of all the different kinds of candy that we have. So this is a two-way frequency table. So I have one category on the side, my types of candy, my M&Ms and Skittles, and then another category across the top, my colors of candy. So we're going to be using this frequency table to answer some questions. So let me move my face out of the way here. So we can compute the probability of an event occurring from the frequency counts within the candy mix two-way frequency table. So find the probability of randomly choosing candy with the listed attributes. So, and these are all in your guided notes, so follow along if you have those. If not, take your own notes. But A says, find the probability of drawing any color M&M. So in other words, in probability set notation, we would write that as the probability of drawing an M&M. Well, this is my column of M&Ms. Remember, when I'm finding a probability, I take the number of times that I could draw an M&M, so there's 266 total M&Ms, divided by the total possible number of outcomes. So the total numbers of pieces of candy that I have is 562. So again, I'm envisioning that I just have like a big tub with all these pieces of candy, 562 pieces of candy in. What is the probability that I would draw out an M&M? Well, there are 266 total M&Ms. So 266 divided by 562, I'm not going to worry about reducing that fraction. But 266 divided by 562 is 0.47, or about 47%. If you wanted to go a couple more decimal places, it would be 47.3%. So almost a 50% chance, about a 47% chance that when you draw a piece of candy out of this big tub, it's going to be an M&M. The next one says, find the probability of drawing a purple Skittle. In probability set notation, that would be the probability of drawing a purple and a Skittle, the intersection of a purple and a Skittle. So let me erase all this. Here are my purple candies, and here are my Skittle candies. How many of my candies are purple and Skittles? Well, 37 of them. There are 37 purple Skittles out of a total of 562 candies. So 37 divided by 562 is 0.066, or if I change this to a percentage, it would be about 6.6%. So there's about a 6.6% chance of drawing a purple Skittle out of this giant tub of candy. Not a super good chance, right? Because there's only 37 Skittles, or purple Skittles. Okay, here's a few more. How about the probability of drawing a blue M&M? So here are my blue candies. Here are my M&Ms. I'm trying to find the probability of drawing blue candy that is also an M&M. The intersection of the blue column and the M&M row, which is 45. There are 45 blue M&Ms, and there's 562 total candies. So 45 divided by 562 is 0.080, or 8%. So there's an 8% chance of drawing a blue M&M. How about an orange Skittle? Well, here's my orange column. Here's my Skittle row. There are 58 Skittles that are also orange. So 58 divided by 562, 58 divided by 562 is 0.103, or 10.3%. 10.3% chance that you draw an orange Skittle out of my big tub of candy. Then the last one here says the probability of drawing any green candy. So here's my green column. I'm not specifying an M&M or a Skittle, just any green candy, the total of all my green candies is 87. I have 87 total green candies. So that's 87 possible green candies divided by 562 total candies. 87 divided by 562 is 0.154, or 15.4%. So there's a 15.4% chance that I'll draw a green candy, Skittle, or M&M out of my giant vat of candy here. Okay, these ones are not in your guided notes if you're following along with my guided notes, but these are extremely important and helpful to be able to identify. So, F here says we're trying to find the probability of drawing a blue candy or a Skittle. So the way that I would write that in probability set notation is the probability of the set of blue candies unioned with the set of Skittle candies. So remember that a blue candy or a Skittle candy, that's all the possible blue candies or all the possible Skittles. So here's all my blue candies, here's all my Skittles. If I was doing an intersection, if I wanted to know the probability of drawing a blue Skittle, I'd need this number right here. But since I'm wanting to know the probability of drawing either a blue candy or a Skittle, it could be blue, it could be a Skittle, it could be a blue M&M, whatever, you know? Okay, so watch this for a second. So there's 108 total blue candies. There's 108 total blue candies, and there's 296 total Skittle candies. So that gives me, let's see, 108 plus 296. That's 404. That's not my answer yet. Let me tell you why. So my 108 here, that was 45 blue M&Ms plus 63 blue Skittles. And then my 296 was 27 red Skittles plus 58 orange Skittles plus 59 yellow Skittles plus 52 green Skittles plus 63 blue Skittles plus 37 purple Skittles. Right? Well, notice here, I counted my 63 blue Skittles twice. I double counted 63 blue Skittles. That doesn't make any sense. I don't need to double count those. So this total that I got, 404 candies, is too big. I need to take away 63 pieces of candy because I double counted 63 pieces of candy, these 63 blue Skittles. So 404 minus 63 is 341. So the probability of drawing a blue or a Skittle candy is 341 divided by 562. 341 divided by 562 is 0.607, or 60.7%. About a 60% chance of drawing a blue or a Skittle. So again, pay close attention to that. What I had to do when I was trying to find the probability of this union is I had to add the total Skittles plus the total blue candies, and then subtract the intersection of the blue and Skittle candies because I ended up here double counting those. Okay, so let's do this again. Let's do another example. So I'm trying to find the probability now of drawing a red candy or an M&M. So let me erase all this jazz. So I'm trying to find the probability of drawing a red candy or an M&M, or in other words, the union of the set of red candies and the set of M&Ms. Well, here are all my red candies. Here are all my M&Ms. If I was trying to find the intersection, so if I was just trying to find the probability of drawing a red M&M, I'd be using this 51 number. Since I'm trying to find the probability of red candies or M&Ms, I have 78 red candies plus 266 M&Ms. But remember, when I add 78 plus 266, I'm adding these 51 red M&Ms twice. So I have to subtract 51. So 78 plus 266 minus 51 is 293. There's 293 possible red or M&M candies divided by a total of 562 total types or total pieces of candy. That gives me 0.521 or 52.1%. It's So there's about a 50% chance, 50-50, that you will draw either an M&M or a red piece of candy. So those are examples of probability of unions given this frequency table. And again, the reason we talk about these frequency tables is because lots of times data is given in this format, in the format of a table like this. Okay, let's do another example. This one is also in your guided notes. So it says, complete the following two-way frequency table, then use it to answer the following questions. So notice here, I don't have all the information given in here yet. I have a two-way frequency table over here in my rows. I have smartphone and no smartphone. So people who have smartphones, people who don't have smartphones. And then up on top, the columns are people who have iPads and people who don't have iPads. Okay, so we see here that there are a total of 28 people that have iPads. So in this column is going to have to add up to 28. So if I have 20 people here that have a smartphone and an iPad, I must have 8 people here that don't have a smartphone but have an iPad, because these have to add up. Same here. If I have 28 total people who have iPads and a certain number of people who don't have iPads, that means I'm going to have a total here of 50. So 50 minus 28, that's 22. 28 people with iPads, 22 people without iPads for a total of 50 people, because this is my sample size. This is how many total people I have here. Same in this column. If I have 38 total people with smartphones and 50 total people, that must mean I have 12 people that don't have a smartphone. 38 people with a smartphone, 12 people with no smartphone, for 50 people total. And then these columns are going to have to add up. So 20 plus what is equal to 38? This is 18. 8 plus what is equal to 12? This is going to have to be equal to 4. So notice all of these, the columns and rows, the totals have to match up. So this row right here, 20 plus 18 has to equal 38. This row right here, 8 plus 4 has to equal 12. This row right here, 28 plus 22 has to equal 50. And then same going down in the columns, 20 plus 8 has to equal 28. 18 plus 4 has to equal 22. 38 plus 12 has to equal 50. That's how these frequency tables are set up, such that no one is missing. Everyone is accounted for. All these totals add up. Okay, so there will be examples like this on your homework where I give you either an empty frequency table or a partially filled in frequency table where you'll have to fill in with the data yourself. Okay, now let's answer some of these questions. What is the probability of selecting someone from this group of 50 people? What is the probability of drawing someone who has an iPad? Well, how many people have an iPad? I have a total, look at my iPad column, of 28 people who own an iPad. So 28 people own an iPad out of 50 total people. So the probability of selecting a person out of this group that has an iPad is 28 divided by 50. Or that's 0.56 as a decimal, or 56%. So 56% of these people have iPads. Okay. Next, I want to find the probability that someone has an iPad and a smartphone. So here's the column for iPads. Here's the row for iPhones. Whoops. Looks like, and I'm looking for an intersection, so I'm trying to look for someone who has an iPad and a smartphone. There are only 20 people that have an iPad and a smartphone. So the probability of selecting someone who has an iPad and a smartphone is 20 divided by 50. As a decimal, 20 divided by 50 is 0.4, or in other words, 40%. So 40% of the people in this group have a smartphone and an iPad. Well, how about this? What about the probability? I don't know why these numbers got all weird. What about the probability of someone who has an iPad and no smartphone? So, well, instead of the row with a smartphone, we're going to be looking at the row with no smartphone. It looks like there are 8 people who have an iPad but don't have a smartphone. So the probability of selecting someone who has an iPad and no smartphone is 8 out of 50. 8 divided by 50 looks like 0.16 or 16%. So 16% of the people in this group have an iPad and no smartphone. Okay, so those right there were some intersection problems with a little cap there. Those are intersections. Now we're going to look at some union problems. What is the probability of iPad union smartphone? So in other words, what is the probability that someone has an iPad or a smartphone? So here's my iPad and smartphone columns. So if I was looking for the intersection, if I was trying to find the probability of selecting someone who has an iPad and a smartphone, I'd be looking at this 20 number. But I just am caring if they have an iPad or a smartphone. Well, there's 28 total people who have an iPad, and there are 38 total people that have a smartphone. But remember, when I add those columns, my iPad column and my smartphone row, I'm adding the number of people who have an iPad and a smartphone twice. So I need to subtract 20 people. 28 plus 38 plus 20, or minus 20, sorry. 28 plus 38 minus 20 is 46. 46 divided by 50, because 50 is the total number of people in this group. 46 divided by 50 is 0.92, or 92%. 92% of the people in this group either have an iPad or a smartphone, or both. How about the probability of no iPad union with no smartphone? So I need to look, let me erase these, I need to look at my no iPad column and my no smartphone column, because I'm trying to find the probability of people who either don't have an iPad or don't have a smartphone, are really technologically deprived people. So there are 22 people that don't have an iPad, and there are 12 people who don't have a smartphone. But remember, with those 22 and 12 groups, I'm counting the group of 4 that don't have an iPad or a smartphone twice. So I needed to subtract one of those sets of 4. So 22 plus 12 is 34, minus 4 is 30. I need to divide by 50, so because I'm trying to find the probability out of the total. 30 divided by 50 is 60%. 0.6 or 60%. So 60% of the people in this group either don't have an iPad, don't have a smartphone, or both. Okay. So that's really the majority of what I wanted to talk about with finding probabilities and reading two-way tables. Now I'm going to do a homework problem from your homework assignment. So tune in. This will be kind of a freebie for your homework assignment. This is homework problem number 3. So I have this two-way table where on my rows over on the side I have the group of boys and girls, and on the top I have the group of London and York. So I have some information here. So it says 80 children went on a school trip. So this is representing a school trip. So the total number of people who went on this trip was 80. 80 people went on this school trip. They either went to London or they went to York. This must have been over in Great Britain somewhere. They either went to London or they went to York. So 23 boys and 19 girls went to London. So in my London column, there were 23 boys who went to London and 19 girls who went to London. And then it says 14 boys went to York. So 14 boys here went to York. So I've kind of filled in the table with the information that was given to me, and now it says use this information to complete the two-way table. So I think the homework assignment is just filling in this table, and then I've added for us to be able to compute some probabilities. Okay, well, the total number of boys that went on this trip is going to be the total number of boys that went to London plus the total number of boys that went to York. 23 plus 14, that's 37. So that's good. Also, I can figure out the total number of people that went to London, because 23 boys and 19 girls went to London. 23 plus 19 is 42. Okay, so remember that all of these rows to the right are going to have to add up, and all of these columns down are going to have to add up. So if there's 42 total people that went to London and 80 total people that went on this trip, that means 80 minus 42 means 38 children must have gone to York. So now I can add up this column. If 14 boys went to York and 38 total people went to York, that means that 24 girls must have gone to York. Then for this last box, if 19 girls went to London and 24 girls went to York, that means a total of 43 girls must have gone on the trip to start with. So that's how I would fill in a two-way frequency table. And the reason I fill in this table is because to compute some of these probabilities, it's really a lot easier to compute them and visualize them given this table. It's a really convenient and pretty way to look at all of this information, all of this data. So now I want us to find the probability that I select a student who went to London on their trip. So here's my column of Londoners. There are 42 total people, 42 total students who went to London. 42 students went to London out of a total of 80 kids who went on this trip. Well, 42 divided by 80 is 0.525, or 52.5%. So 52.5% of the kids on this trip went to London. Now I want to find the probability of, and this is kind of in probability notation, this is the probability of York intersected with boys. Or in other words, the probability that I select a student who is a boy that went to York on this school trip. So here's my York column. Here's my boy row. The total number of boys who went to York is 14. I'm trying to find the intersection. So I'm finding where both the column and the row intersect. So there are 14 boys that went to York out of a total of 80 kids. 14 divided by 80 is 0.175, or 17.5%. So 17.5% of the kids on this trip were boys who went to York. Okay, now I want to find, this last one is the probability of London Union girls. Or in layman's terms, I'm trying to find the probability of selecting a student from this group that either went to London or was a girl. So anybody in this column that went to London or anybody in this column that was a girl. So it's possible that I select a person in this group who was a girl who went to York, or a girl who went to London, or a boy who went to London. Either or. So notice here that there are 42 people that went to London, 42 of these students, and there were 43 girls. But notice again, when I add those two totals, the London group and the girls group, that I'm double counting these 19 girls who also went to London. So I have to subtract 19, so I don't double count it. 42 plus 43 minus 19 is 66. So 66 out of a total of 80 students either went to London or were girls. 66 divided by 80 as a decimal is 0.825, which is 82.5%. So 82% of the kids in this trip either went to London or they were girls. Okay. Another real quick important thing to remember when we're talking about probability is all the probabilities when you have a decimal will be between 0 and 1, or as a percentage, all your percentages will be between 0 and 100%. If you get something more than 100% or less than 0%, that's a pretty good sure sign that you did something wrong. Okay, that was everything that I wanted to discuss in this lesson. Again, this was all about using two-way frequency tables to compute probabilities. So hopefully now you feel comfortable to construct a two-way frequency table if I give you some data. Hopefully you're able to compute individual probabilities given a two-way frequency table, and also compute probabilities for intersections and for unions using a two-way frequency table. So I hope that was helpful. Please let me know if you have any questions whatsoever. Please reach out to me, and I hope that you enjoyed that as much as I did.